presented by Caltech.
Welcome to the 4th annual Neugebauer Lecture. This is one of the two main events our department has every year, the other one being the Greenstein Lecture. This series celebrates life and work and legacy of Gary Neugebauer, a late professor of physics and pioneer of infrared astronomy. Gary got his PhD at Caltech in 1960, I think, in particle physics. And then he worked at JPL in the early planetary exploration of Mars during his military service, became Caltech faculty in 1962. And with the other famous Caltech professor, Robert Layton, he decided to start exploring infrared sky, which was very much a new frontier back then. They built a small special purpose telescope at Mount Wilson to do this. And with it, they did the first infrared sky survey, the 2-micron sky survey, not to be confused with 2-micron all sky survey from 1990s. Theirs was the first, only 5,000 sources, but it was a new frontier. Gary started a world-class infrared astronomy group, who pioneered many things, with his then student Eric Becklin sitting there. They discovered a thing called the Beckling-Neugebauer object, a very luminous source in Orion, which we now know is a dust-obscured protostar, the first one of a kind. They did mapping of the galactic center, many other things. In 1983, Gary and his group, which also includes our own Tom Sofer, Keith Matthews, and others, were principal behind the IRAS satellite, which revolutionized our understanding of the infrared sky. And even today, this is also why we have IPAC here at Caltech, which is also NASA's premier center for all things infrared and also exoplanetary. Gary served as the division chair of physics, math, and astronomy, as the director of Palomar Observatory. It was crucial in the early days of Keck. With his group, they developed a lot of pioneering infrared instrumentation. He received a number of important prizes and honors, Rumford Prize, Norris Lectureship, Herschel Medal, Bruce Medal, member of both National Academy and American Academy of Arts and Sciences, and so on. So he certainly left a major imprint both to the world of astronomy and Caltech. Well, today we're very happy to greet our distinguished speaker, Dr. Franz Córdova, the director of the National Science Foundation. Franz was actually born in France, in Paris, but grew up in California as the oldest of 12 siblings. And she thus took care of the other 11, which must have been a great preparation for some of her subsequent jobs. And her academic career started with a bachelor's degree cum laude from Stanford in English. And then she did some field anthropological work studying the Zapotec people in Oaxaca, after which she wrote a short novel that was well received, a cookbook, and worked as a temporary editor of the Mademoiselle magazine. At which point she decided she would like to do something more challenging and interesting, and to become an astrophysicist. In 1979, she received PhD in physics from Caltech, working with Gordon Garmire and Jesse Greenstein on some of the pioneering work in X-ray astronomy. After which she went to Los Alamos, starting as postdoc, ending up as group leader. And after 10 years there, she became chair of the Department of Astronomy and Astrophysics at Penn State. By 93, she was also named the vice president, but then she had a better job offer, and she became the chief scientist of NASA, the youngest person ever to hold a title and the first woman, where she fought mightily to preserve the existence of NASA's Science Center, successfully at that, and was recognized by the NASA Distinguished Service Medal for that work in '96. She then moved to UC Santa Barbara as professor and vice chancellor for research, and from there to UC Irvine as the chancellor and also distinguished professor. And then in 2007, became president of Purdue University, where she did a lot of important initiatives. And they even named a new recreational sports center after her because she was so instrumental in doing it. You know, so people can get the astronomy prizes, but can you get a sports center named after you, right? She became member of National Science Board in 2008, of the Board of Regents of Smithsonian in 2009, shortly becoming the chair of that board. And in 2014, she became the director of the NSF, where she is still now, where she is not only a powerful advocate for science, but also for social issues in science. And I have to read to you something that happened today. This morning, House Science Committee had a hearing about combating sexual harassment in science. And the ranking member, Frank Lucas, a Republican of Oklahoma, I think, said this: I commend the National Science Foundation for already making changes. Under the leadership of Dr. Franz Córdova, NSF has set new policies to address sexual harassment and ensure the safety of all grant personnel, supported by taxpayer funding. Our legislation process that these types of processes should be adopted by all federal science agencies. So Franz received a number of prizes and recognitions, including being 2007 Distinguished Alumna of Caltech, Kilby Laureate Women's Science Award, Fellow of Top AAAS, American Women in Science, of American Academy of Arts and Sciences, National Academies, and at least 6 honorary doctorates. So at this point, you might get an idea she's a little bit of an overachiever, and you'll be right. And so without further ado, let's welcome Dr. Franz Córdova.
Thank you, George, for that very, very generous introduction. It's just such an honor to be giving this talk in celebration of a person that we all share a tremendous admiration for, Gary Neugebauer. So first of all, can everybody hear me using this mic? Because I have other mics up here. There's a lot of stuff up here. So I could never have imagined when I was complaining to Gary about troubles with my thesis project, or laughing when he was exasperated by something unexpected happening in the laboratory, that one day I'd be standing here giving remarks in his honor. So let that be a lesson to you graduate students. You might want to start taking notes right now about some of your mentors, and also mentors, just be aware. Because these stories all come back someday. So I did quite a bit to prepare for this speech. I lived another 40 years so after graduating from Caltech. So that journey has brought me to this moment when I can reflect fondly on what Caltech gave me and how those gifts have propelled me over the decades. But first, let me see if I can, there we go. Okay, turn the slides, yes. So. But first, I want to give a few recollections of my own graduate student career at Caltech, and hope that some of this resonates with you students in the audience. My background, as George said, was a little bit different for Caltech. I was an English major, very little science training. I had one course in college astronomy, no math. After college, I went back east to Cambridge, Massachusetts on a grant to do an education project, it turns out, with 3 Caltech graduates. Inspired by a TV show about neutron stars, I went to nearby MIT looking for summer work. And they hired me. I spent a few months there at the Center for Space Research analyzing balloon flight data. It was the earliest days of X-ray astronomy, as extraterrestrial X-ray sources had recently been discovered with sounding rocket flights. As an English major, I was asked to help edit a review article of this new field, and I secretly suspect that's why they took me on in the first place. But it turned out to be a great introduction to a whole new field of scientific inquiry, and led me eventually to becoming an X-ray astronomer. But by fall, I moved back home to California and my family. And eventually, I found my way to nearby Caltech. My family, in fact, lived just down the road on Oak Knoll Avenue. I knew of Caltech, of course, and its X-ray astronomy group there because of working on the review article. I inquired about a job with the X-ray rocket group that was headed by Gordon Garmeyer, headquartered in Downs Laboratory. And he gave me the job, and he handed me Chandra Sekhar's book on radiative transfer and told me to translate it into code for an upcoming satellite project. So at the time, I didn't have any computing experience, but the graduate students in whose office I landed were very supportive, and the Fortran 4 manual was easy enough to follow. So at the same time, I took background courses in physics and calculus at Cal State LA. And then the following year, a few professors at Caltech, including Tom Tombrello and Gordon Garmeyer, others, said I could audit their courses and see how I would do. Well, I did well enough that they then admitted me into graduate school. I think part of the reason I succeeded, for example, in electricity and magnetism, is because there was an essay requirement. Few knew how to write essays, using only Jackson's textbook as a guide, but with my English background, I did. There aren't many ordinary mentors or colleagues at Caltech. My math teacher, John Matthews, had written with Caltech's Robert Walker the textbook, Mathematical Methods of Physics, and he coached me when I failed my first math exam. My instruction was to meet with him once a week and go over his book. The professor in the office next to mine and my occasional hiking buddy, Bob Layton, wrote the textbook on principles of modern physics. And that's Caltech. That's how lucky you all are. I was privileged to learn from the people who were shaping the fields and writing the textbooks, and they all made me feel that I would succeed. Together with my fellow graduate students, I put together rocket payloads and then went to the White Sands Missile Range in New Mexico to launch them. And we went without our advisor, who believed that you should sink or swim. And so we did a lot of both. We strapped the payloads in the rocket with duct tape, and we watched them rise into the night sky. And then we hurried into bunkers to see our data on black hole candidates, secreting white dwarfs, and the like. I had a near-death experience on the launch pad during a violent thunderstorm, but if the graduate courses in physics didn't kill me, neither could a payload twitching with current running through its bolts. At the time, I had an office on the 4th floor of Downs Lauritsen, and so did Richard Feynman, my instructor for quantum mechanics. His office was past the elevators on the Lauritsen side. His van was parked outside, painted liberally with Feynman diagrams. Some of you here may remember that van. He and Murray Gell-Mann, who also had an office on that corridor, would tell students how they had no time for research now that they had their Nobel Prizes. And I thought, well, life is tough for some. I attended a lot of visiting lectures by prominent scientists, and I went for the cookies, as students do. One significant person, faculty member I remember giving lectures, was Peter Goldreich, who had a habit of coming to the podium looking completely underprepared or not prepared at all. And he would dig into his back pocket and pull out some scraps of paper and lay them out on the desktop and then just give a brilliant lecture. So that was kind of our role model there. On the weekends, I rock climbed with the other students. A Caltech engineering professor, Chuck Wiltz, wrote the Climber's Guide to Talkeets and Suicide Rocks, and it was there that I spent a lot of great moments. One of my fellow students used to build her up the side of Millikan Library. I don't think they let students do that today. In those days, we had a batch computer center on campus. I don't know if you students can visualize what that might have been like. Everybody used punch cards. We carried around these big boxes as such. It turned out to be the location to find a new friend. I also made a lot of friends jogging around the track, where usually somebody running at my pace would jog with me. And that was how I met Claire Patterson. Only later did I find out about his significant work detecting lead in the Arctic ice and also determining the age of the Earth. That was Caltech to me, the most seemingly ordinary, fun people people just jogging around the campus, playing tennis over here on the courts, had extraordinary lives. My toughest experiences were polishing and testing flats for X-ray reflectivity in the basement of the old synchrotron lab, using parts of the old synchrotron itself. I complained so frequently about this tedious task that my thesis advisor didn't think I'd amount to much. I much more enjoyed nights on the mountain in the company of the infrared astronomers. It turns out that the infrared group, headed by Gary Neugebauer, was housed on the same corridor of Downs as the X-ray group. Gary and Gordon Garmeyer had a rule. Every graduate student office had to have one IR and one X-ray student in it, so that we could expand our understanding of tools and discoveries spanning more of the electromagnetic spectrum. The infrared astronomers were also very interested in identifying the new sources of X-ray radiation that were being discovered all the time. In those days, IR data were taken on strip charts. I don't know if you students have ever seen a strip chart, but that was just wiggles back and forth, and you can see sources as you scan over them. The quality of the night sky was determined by hoisting oneself on the dome of the 24-inch at Mount Wilson and rotating round and round. Discoveries were made regularly, new nurseries of stars, new rings around planets in our solar systems, even new solar systems, and of course, the identification of new X-ray sources. My most memorable experiences came from making observations on mountaintops, Chile's Cerro Tololo, Palomar Mountain, and Mount Wilson. I was surprised that at Mount Wilson, all the senior astronomers had napkin rings with their names embossed on them, and the seating was done in the order of the size of the telescope that you were observing on. I tried climbing the outside ladder on the big dome at Palomar until Gary ordered that I be stopped. In Chile, I ran between mountaintops because I thought the freedom felt great, and lots of the astronomers did that. One year, while doing part of my dissertation work at Harvard SAO, I entered the Boston Marathon. This was, I think, the year before runners were required to qualify, so anybody could jump in. Although friends said I couldn't do it, I put one foot in front of the other, and I finished. And the lesson learned was don't believe everything your friends say that you can't do. My Caltech experience was immensely supportive. The laboratory research was very hands-on. Professors worked with the students in the lab or at the observatory. My appreciation for this nurturing environment was rivaled only by my excitement over the subject matter. I loved the class of stars I studied, which were cataclysmic binaries and accreting neutron stars and black holes. Anything compact and degenerate was fascinating. I was fortunate to be among the first wave of young astronomers who worked with amateur astronomers worldwide to follow the outbursts of these stars to see if X-rays could be detected in coincidence with visual brightenings. And they could. My dissertation was sealed when I discovered pulsing X-rays from two of these objects had gone into visual outbursts. My thesis comprised 5 published papers that I stapled together with an introduction. The acknowledgments section got more attention than the thesis itself, so score another point for the English degree. Through all of this, I had 2 mentors, T.S. Eliot, the poet, and Gary Neugebauer. I'm not sure which helped most, feeling sorry for myself in the wasteland, or Gary's benign amusement at my travails. In 2 days, I'll be giving the Caltech commencement address. Lucky me. I'll talk about Caltech's influence on my career or careers. So today, I'd like to talk about my role in 5 administrations, what I did and what I learned, and I hope that what will shine through are the value and rewards of public service that I've gained along the way. My first presidential appointment was from George H.W. Bush. It was while I was at Penn State. It was to serve on the National Medal of Science Committee. From that experience, I learned that you have to be nominated to win a prize, and it helps to have champions on the prize committee. I was such a champion for astronomers and continue to be so to this day. I also learned that one thing leads to another. The chair of that committee recommended me to the head of NASA, who was looking for a chief scientist. So earlier today, when I was with the students, and I've had several meetings with students today, I was asked just how many things should you accept to be on, and I said you should accept some things with discretion because they do lead to other things. And in fact, everything that I think I've done, every significant change has been because of doing some other form of public service and being recognized for that. I served as NASA's chief scientist during the Clinton administration. And I'm still friends with the then NASA administrator, Dan Golden, who's the longest serving NASA administrator. So I couldn't have done too poorly. We had a lot to do. He really started pumping money into the great field of astrobiology. And it was my first introduction to science policy. And it was also my first introduction, of course, to working with other federal agencies and seeing how policy really got done. Among the highlights of this experience were the first Hubble rescue mission, missions to Mars, working with astronauts to communicate the importance of human spaceflight, persuading Congress to approve a new South Pole station for the National Science Foundation, and getting Congress to vote, I think it was by one vote, for a new International Space Station. And also chairing a committee that corralled federal science agencies to agree on a common definition of research misconduct. The conduct of research and the health of the research environment is also something that has really interested me in addition to scientific research itself. I learned that it takes a long time to get things done across agencies, but when they get done, it takes even longer to undo them. I also learned how very important Congress is in securing the budgets for the science agencies, how important it is to educate our elected officials about the goal of science and its benefits. And mostly, I learned that making progress is a team effort, an idea I also learned from being a soccer mom at the same time. And to think I didn't even know what the word policy meant when I went to NASA. While I was at Purdue, I received a presidential appointment from George W. Bush to serve on the National Science Board. And later, and that was at that time a Senate-confirmed appointment, and later a commission from President Barack Obama to serve as a regent of the Smithsonian Institution. Those appointments gave me a fabulous insight into NSF and the Smithsonian and led to my present position as director of the NSF. Appointed or nominated by the President in 2013 and confirmed by the Senate in 2014. And that was because of my service on the Smithsonian, where people there recommended me to the administration. So one thing really does lead to another. And although he didn't appoint me, President Trump didn't fire me. So I can actually say that I've served science and science policy in 5 administrations. So what have I learned from that large dosage of public service? So the rest of my talk is going to be on things I've learned and how the science policy infrastructure is constructed in the federal government. So first, I've learned that relationships matter, and good relationships are key to getting things done in Washington. Respect for others goes a long way in securing these relationships. And this takes time, it takes a lot of time, and a willingness to sit and listen. I have people going through my office almost every day, certainly a few a week, people who are heads of other agencies that I work with, people from the administration, from OSTP, the Office of Science and Technology Policy, from the Office of Management and Budget. We have a lot of visitors from other countries who are ambassadors, leaders of research agencies, even vice presidents of some of the smaller countries. All of them are intensely interested in how the science engine works in this country, and all figure that they have a lot to learn from the National Science Foundation. I've learned that most elected officials care deeply about science and want to ensure that the U.S. is first among nations in science, engineering, and technology. So that's true almost to a person, that everybody I've met with, and I meet a lot of elected officials. There was one period of 2 months, about a year ago, that I visited, I had 70 individual visits to senators and congressmen to talk about the National Science Foundation and its plans. These people are, however, limited in attention and funding by many competing priorities, some of them quite urgent. I've learned that it helps to have a vision of where you want to go and a plan. And so some of you heard a couple of years ago, I talked about the National Science Foundation's 10 big ideas. So I'm certainly not, we don't have all night here to talk about 10, but I thought a few of them, we've made so much progress in the 3 years since we first introduced this. I thought I should just mention a couple of words about a few of these. The 3 years ago was the genesis of what we call the big ideas, and there are 10 of them. 6 of them are research ideas and 4 are enabling ideas. And we were in an environment where NSF was in a bit of a crisis mode. There were some people that were complaining in Congress about some of the projects we funded. They didn't like them. We ended up in their waste books, so-called waste books, and we felt like we were always playing defense. And as you know from sports, that's fine to have a good defense, but you don't score any goals that way. So we thought we really had to turn the tables on that. So with the help of the National Science Board, which is our oversight policy arm, and there's one member, Anila Sargent, of the National Science Board, who is in this audience, we were urged to go on the offense and construct a strategic plan for the future that would captivate the imagination of our elected officials, the administration, and the public, let people know where we were going, put up signposts to a transformative future. This was a novel approach for the National Science Foundation. We're a very bottoms-up organization, have been so for nearly 70 years. And we get good ideas in, we triage them through a merit review process that other nations copy. It's a very good process. And we are curiosity-driven, fundamental research, progress of science is our mission, and so on. But we thought it was, in this day and age, people want to have some idea of where you're going, what's important to do, what's important especially to invest in, and what are your priorities. So we got all the ideas from all the groups around the agency together, and we set out some big, broad-based directions. So it resulted in these 10 big ideas, which is not a unique set by any means, but it was an inspired set, because some of the big ideas, mind you, when we first postulated them, it was before the last election. Some of them have turned out to be administration priorities, like our quantum leap goal to invest more in quantum-based research. Our artificial intelligence is an administration priority goal. Cyber security and everything cyber is another goal. All of these are embedded and in fact, substrates of our big ideas. So we caught these trends early enough to position the U.S. as a global leader, and now we have friends all over the Washington policy environment that are really very, very much enamored of these goals, and we have a lot of committees and all, as I'll describe in a moment, to further them. So about these 4 pictures that I put up here, I think you all know, because there's a large number of astronomers, astrophysicists in the group, that we have one of our big ideas is called Windows on the Universe, the era of multi-messenger astrophysics. So it's, of course, the first time on the planet when we not only have a large suite of electromagnetic facilities to observe the universe, but we also have particle detectors like the ice cube detector for neutrinos at the South Pole that you see in the picture on your left at the bottom, and of course the gravitational wave facilities that have done so well in the past few years. So putting all of those together, we can, we think, make extraordinary discoveries. And that's been borne out in at least two very key observations recently. One is the detection of the neutron-star merger by LIGO and by a large suite of ground-based and space-based observatories all over the world. And then the next was the discovery of neutrinos by the IceCube experiment at the South Pole at the same time that high-energy gamma rays were observed by ground and space-based observatories, and put together a picture of a blazar that was flaring at the time that showed that at least one origin of high-energy cosmic rays was from active galactic nuclei, thus solving, at least in part, one of the outstanding mysteries of the last 100 years of what is the origin of high-energy cosmic rays. So there are other lessons that we got from these experiments and getting ready for them that I'll describe as I go along. But one is if we jump across to the bridge there, the bridge that has a big gap in the middle, one of our big ideas is in response to where are the gaps in what we're investing in. And a significant one is in the area of mid-scale facilities. That is, we didn't have a program dedicated to funding facilities that cost between a few $1 million and $100 million. And yet there's an enormous amount of creativity in this. And two examples are that before the IceCube detector was built, we had something called Amanda experiment at the South Pole. It was the precursor to IceCube. And it was, the amount of money it spent was in that regime. Another example is LIGO A+, which is money that, about $20 million that NSF has given recently to upgrade the present LIGO experiment to be able to have reduced noise, much more sensitivity to a greater volume of the cosmos. And so those are just two examples. There are many, many others. The Event Horizon Telescope costs something less than $30 million, so it would fall into that range. The Zwicky Transient Facility, which can be viewed as significant on its own and also as a test bed for the upcoming Large Spectroscopic Survey Telescope, or LSST. There's just a wealth of invention in this gap. And we committed to funding it, and we put out a solicitation a few months ago, and the response was extraordinary. We got $5 billion worth of great proposals to fill that gap, $5 billion. So it just shows when you can do things when you have an open mind to what you're not doing and what gaps really need filling that can tap into the imagination, the creativity of scientists and engineers. Then in the middle there, I have another one of our big ideas, which is harnessing the data revolution. We were committed to funding data science, all the big telescopes of the world, and big everything, big ships. Ships are a tremendous amount of data being collected there. The high-performance supercomputers and all people that want to run simulations and so forth. There's just large, large volumes of data, and we don't yet have all the techniques to exploit data analytics and data archiving and in any way that's efficient and effective and not so expensive. So we have a lot of opportunities and solicitations out to do a better job with that. The examples of how this is connected, of course, to astronomy are abundant. I don't need to remind anyone here of the example of numerical relativity and how much the identification, well, exclusively of the sources that were detected by LIGO depend on computation that came about because of engaging the numerical relativists in that. So harnessing the data revolution is one very big idea that deserves a lot of extra funding. And then I have one more example here, which is the NSF Convergence Accelerator. It's not one of the big ideas, but it's a spin-off from the big ideas. It's our effort to try to deliver to an administration that is really concerned about action now. They don't want to wait 100 years for general relativity to become GPS or discover gravitational waves. They want discoveries to be translated, at least some of them, as fast as possible. And we recognize that we can accelerate research. We've had our Innovation Core program now for 6 or 7 years. It's resulted in very fast translation of discoveries to the marketplace and in more than 500 new startups. So we devised the idea of having a publicly funded accelerator that would be somewhat similar to private accelerators like Techstars or Y Combinator, but this would be an opportunity for cohorts of teams to get together around focus areas and really apply all their creativity towards those areas and see if they could accelerate research in those domains. So quantum, devising the first practical quantum computer that has 100 qubits instead of a few qubits could be an example in this area. We have one opportunity right now to develop techniques for interrogating databases that would be interoperable. As you know, in astronomy, we have loads and loads of databases for all the different kinds of science, but it's very hard for people outside the domain to easily access them and make sense of them all. Let me give you one example, going back to harnessing the data revolution, of the importance of open access and having large data immediately available to the world and the discovery potential. I was about 2 weeks ago at Princeton giving something called the last lecture to the students there. And I, in going around the Institute for Advanced Studies with their leader, Robert Digraph, I met 2 enterprising young astronomers from abroad who had taken all the LIGO data and were from runs 1 and 2 and reanalyzed it. And so that immediately struck fear in my heart. I said, I wonder if they actually rediscovered the sources that are out there. And I asked them, and they said, oh yes, and we discovered 6 more sources that that hadn't been found yet. And so they've published, so that's in the open literature now. But it just shows you that when you do make your data open and accessible, and bright young people with maybe better, different algorithms for reducing noise can find new sources in them. So so what else have I learned? I've learned that investing in projects for the long term in basic research can have huge payoffs. So as I said, we have a society that is driving us towards very short-term results. And yes, research can deliver something. If it's up to a certain level of technology, it can be speeded up and we can have short-term results. The chances are higher that those will be more incremental results and not necessarily transformative results that you can get by sustaining your investment over a very long time. So that is what we've done with the 3 examples here in the face of a lot of questioning about whether these experiments would even work. These discoveries, the discovery of merging black holes and neutron stars, the discovery of high-energy cosmic rays neutrinos from a blazar or an active galactic nuclei, the imaging of a black hole for the first time. These were experiments that took a very long time, decades really, and a lot of careful work. And they, though they seem magical, they really aren't magic. It was just plain old hard work. They had long incubations. They really required, at the National Science Foundation, stalwart program officers. So in February of this year, there was a nice article in the New York Times by Dennis Overby, who those of you who read him, no, he's a wonderful writer. And the title of it was, "In Science and in Sports, the Sidelines Matter." And this article went on to describe what is in baseball and other sports known as the Hot Stove League. He called it for science, the Hot Stove Science League, which describes the people behind the scenes. He said, quote, "LIGO was a saga of persistence, ingenuity, and professional skepticism." And that it was indeed, especially if you read, as I have done, the oral histories of the period of the 90s and seeing just what a struggle it was to get from there to here. But there are people who belong in principle to that Hot Stove Science League whose names you don't see or hear of, but they are the ones who fight the battles for continued funding, fight the skepticism. So I now want to transition into what I've learned about science policy. I've learned that policy, as I said, a word that I wasn't very familiar with when I went to Washington first time in 1996, is really important for building on the research that we invest in, giving it context. And it is important to communicate to our nation and other nations what is important to us, what is of value of us. It gives what we do a structural framework to operate in, and it can often overcome barriers to science and the progress of science. And I gave one example earlier today to a group of people over at the Carnegie Institution about the radio and optical spectrum, which, as you know, is threatened by a lot of stuff going up there, including the most recent bevy, a large bevy of small satellites, communication satellites to increase broadband, which are making a lot of light in the night skies, and also have a lot of potential, the auctioning of the electromagnetic spectrum, to interfere with radio observations on the ground. So all of these things take coordination across the federal agencies, and then they take coordination across other branches of the administration. So here I show the main science policy arm of the administration. It's called the National Science and Technology Council. Technically, the president presides, but always in practice, it's the head of the Office of Science and Technology Policy Director, who now is Kelvin Drogemeyer, a good friend to NSF, our former vice president of our National Science Board. And he's been on board since January, is providing a lot of leadership. But we've had this structure in place for a very long time, and it has 6 committees and then a special committee. These are the main workhorses of science policy. So I just want to say a couple of words about this because I think it's important to know where this kind of work gets done. First of all, I will say before I forget it that all the ones in light blue are ones that are co-chaired by yours truly. So I co-chair 4 out of the 7. So NSF definitely has a voice in shaping science and technology policy in this country. There's the Committee on Environment and on Homeland Security and the Committee on Technology, which I do not co-chair. So, and at the very end of the spectrum is not one of the actual sustaining committees of the National Science and Technology Council, but it's a select committee because it's an administration priority on artificial intelligence, and I co-chaired with that with the head of DARPA. So just to give you an idea of what a couple of committees do, on the Committee on the Science and Technology Enterprise, which is new with this administration, there's emphasis on lab to market, and I've mentioned some things about that already. Our I-Core program, Innovation Core program that's all over the country now is an important stable of that. The networking, IT, R&D, they're shaping new policies on open access. Research business models, obviously important. R&D infrastructure and international S&T. And then the Committee on Science, which I co-chair with Francis Collins and OSTP, has an open science, physical sciences, biological sciences, and I would say the most emphasis recently has been on quantum information science. We've already had a couple of summits together with the administration from university campuses, and also one with industry on how we can make progress and ensure our status as a world leader in quantum information science. And then there's always new things that happen when new people come to town. And so Dr. Drogemeyer, in assuming the leadership of NSTC, has devised a new subcommittee, which is a blend of two of the committees, the Committee on Science and S&T Enterprise. So I, just by default, also co-chair that one. And this is a very important one to mention because usually when we think of science policy, we think of science, of research, and engineering technology, but we don't think about the broader landscape of the environment in which we all do science. And I would say of all the new things that have happened in this day and age, as far as awareness of universities, the government, industry, it's that the environment that we live in and work in every day, also we need to take accountability and responsibility for that environment to make sure it's nurturing and supporting, and that we're not letting people go and leave because they're so frustrated with that environment. Because the evidence is that we then lose talent and creativity. And so I'm proud that, that there is this emphasis now on the research environment. This has 4 components in it. One is on research integrity, and that is that is an effort that I would give a lot of credit to the National Academies of Science and Engineering and Medicine on providing leadership and a platform through its many reports on research integrity there. There's a working group on safe, inclusive research environments, and that includes harassment in all its forms, including sexual harassment. And that is a place where NSF has taken a lot of leadership. And the bill that was proposed this morning by the House Space Science and Technology Committee is to have all the agencies adopt the same kind of policies that NSF has adopted. And then on research and R&D protection, research and development protections, this is all about one of the major issues of our day, which is on science and security. I don't think there's any topic that I spent more time on in the last few months than what is our environment, what does it look like now, and what is it going to look like with respect to competition from other countries. We all know that an open scientific environment in which we have generously made our seats in our universities and in our research agencies available to the world, and our data and our science and technology has all been to our credit, and we are a great nation in large part from the contributions of others and working together in international ways. We are more and more aware that some of that feeling of security, it may be misplaced, that there are all sorts of instances, well-documented instances of abuse of an environment of respect and co-sharing internationally. And so their agencies have different postures on this, and I think you've all seen some things in the news about actions that other agencies have taken, like the NIH and the Department of Energy, even in this week, earlier took some new stronger actions to protect intellectual property and to protect people from working in 2 different places and not disclosing it and that sort of thing. NSF has so far, we're taking a very measured approach there. We've hired the Jasons, and Tom Prince is in the audience here, which we think is a very important thing. We don't want to just talk abstractly about risks, and it's all about risk, but we want some concrete definition of where the risks are, what it is that we should be worried about, what we shouldn't be worried about, where to put the emphasis. And so we're really looking forward to the Jason's doing a summer study, which I think they've already commenced, and provide some information not only to NSF, but really to the whole country on how to look at this in a very decisive way. And we're also going to come out soon with our own remake of what's required in a bio profile, so that people have the opportunity to disclose everything, and then we have the opportunity to evaluate those disclosures. Right now, I think people are very confused over what to disclose. But I spent more time on this item because it is such a big, hot topic, and our biggest fear is that agencies which are only concerned about the one-off cases, and there are plenty of one-off cases, will do something drastic to the research environment that we've all grown to love and benefit from in a tremendous way, and our country owes much to. And so it's all a question of balance, and we think that by taking a measured approach that we can achieve that balance. We have the good people to weigh in and help with that. And the last item is on the ever-present administrative burdens, which I think you're all familiar with, how long it takes to satisfy all the compliance regulations. So the administration wants to do something about that. And so our major form of output on all this science policy making has been in reports that look like these reports. These are all from the last couple of years. And they are reports that cover everything from deep science studies and decadal type reports. Recently we had a Frontiers of Material Research, which was a decadal study. We're all looking really forward to the next decadal study from the astronomy community that will help shape, for NSF at least, our directions for the next decade. We've had reports that we funded on reproducibility and replicability in science. That's a new one that just came out from the National Academy of Science. Of course, the sexual harassment of women, the most downloaded report ever of the National Academies, was funded largely by NSF and also contributed to by other agencies. We have a strategic framework for quantum research, for artificial intelligence, and so forth. So there's a large number of topics, and the reports aren't everything, of course, but they are a starting point. They are a way of all the agencies, and there are always about a couple of dozen agencies that come together and agree on these things, so it takes a while to do that. And the administration, of course, because they are coming out of the White House, has to approve them. But they are ways of telling the entire nation and the world what it is that we value, how important they are. It is a way of positioning ourselves so that we do maintain global leadership. And then I've learned that communicating science is our best tool for communicating, or for garnering more public support. And here's an example from the recent Event Horizon Telescope result on imaging the black hole. And I have to share with you that, well, first of all, as you know, this was on the front pages of every newspaper around the world. And in fact, we have a big montage of that in one of our meeting rooms that somebody made for us in every language you can imagine. Recently, the Chief Information Officer of the United States told me it was the most downloaded image in history. So it's a good example of the whole process of communicating science to the public. I have to say that there are major discoveries all the time. You all know that. I know that. And they're not only in astronomy, although it seems like we've had a lot of them in the last few years in the astronomy world. But unless you really take the time, and believe me, putting on press conferences, 8 of them all over the world, simultaneously, to the minute, simultaneously, was a huge effort that took, it was a year in the making. As soon as the EHT group had their image, then they had a long time in which they had to have it peer reviewed, of course. And so that gave us the time to shape the public announcement of it. And I give a huge amount of credit to our public affairs team and to one person who leads that effort, a young person, probably the same age as a lot of the graduate students here, who just single-handedly convinced us, all starting with me, but the whole agency, that because it was an image, that this is the thing that would resonate with the public. This is the thing that would resonate with the whole world. And she was right. I like personally the waveforms, and I like spectroscopy, and but this was it. And she got everybody around that, and it just had a tremendous effect. Part of NSF's job, I feel, is to go full steam with that communication to the public, and a failure to do so would be a dereliction of our duty. It's not only to fund great research, but we have to see that the people who are paying for it, the taxpayers ultimately, and then the officials that they elect that approve it in Congress, that they understand what it is we have done, what is being discovered, and how important that is. And when they see something like this resonate, they are tremendously excited. So much so that one of the committees of the House had a whole session devoted to this observation. So usually we just get interrogated about the budget. So it's really nice to get to talk about science for a change. And your own Katie Bauman was one of the panelists in that venue. So I've enjoyed every aspect of my career, and you heard from George about the different steps, but I think none more than my public service. I've worked with creative, hardworking people dedicated to our mission. I will admit that the federal government is not the most agile of entities. It's slow. People told me once that NSF sometimes stood for not so fast. And process is sometimes overemphasized to the detriment of content. In fact, I've seen some potentially really good ideas, good programs that were launched but just fell under their own bureaucratic weight. So I think a perfectly reasonable idea can take so long, it can become so encumbered by the desire to have simply everybody agree on it that it just really never gets off the ground. But with some persistence, it is possible to set new ideas in motion and to nurture them even for decades, as you've all seen, as they grow and mature technically, even through a lot of naysayers. Investment in originality can be protected by an army of enthusiasts, even in the face of adversity from many sectors. I think of LIGO and its many detractors and the people like program director Richard Isaacson, who saw it through decades of turmoil, and he was recently given an award by the American Institute of Physics for that persistence. Today, our NEON project, the National Ecological Observatory Network, that we spent almost $500 million on, is under similar scrutiny, and I think we have to persist. We have to get it right. I also think of the original engineering centers of 30 years plus of fame when they first started under Eric Bloch's leadership. A lot of naysayers, and now they're just tremendous. Oh, sorry. Okay, did I lose?
Just asleep.
Okay, good. All right. So that's all right. That's fine. That's my final slide anyway. We're going to begin and end with Larry. So there's always people who want to discredit a novel idea, to label it as a waste, but one hopes that the best high-risk, high-reward ideas are recognized as such and protected. And that's really part of our job in the federal science agencies, is to do that nurturing and protecting. Our proof is in the breakthroughs. NSF has funded 236 Nobel Prizes to date. So NIST brags about their 4. I say that's great. Walt, Copan, great, but 236 Fields medals galore, the Genius Awards. This is evidence that our strategy in the merit review process is a good one. So now the biggest threat to investment in basic research looms. It's not the proposed budget. Actually, the proposed budget by the recent House mark is very, very good, would put us at a very significant level. It's not China, and it's not some artificial intelligence robot. I think it's apathy. the result of a failure to recognize the importance of our investments in basic research. I still correspond with a former college roommate. She ends every message with this phrase, which she got out of some manual, quote, "Sent from my iPhone, which is a wonderful byproduct of entrepreneurial free market capitalism. Competition, hard work, innovation, and lack of government interference made this email possible." So she doesn't know all the technologies in our iPhones are the result of government investment. If you go to the AAU website and they have that exploded view of all the components of the iPhone, every single one of them you can trace to individual investigators that were funded by some branch of the federal government. She doesn't know that GPS itself, which lets her know where she is at any time, depends on the equations of general relativity and is owned and operated by the US government. And that she can use Google, thanks in part to NSF, which funded its founders when they were graduate students starting the company. Investments like these have enabled researchers to think big, to stretch beyond the limits of their own imagination, and to follow where curiosity alone may take them. It's that freedom to think big which Gary and Caltech taught me, and which we must all protect for the benefit of science and society. So we have more work to do. Thank you.